Picture the end of the universe, stars burning through their final fuel, matter drifting infinitely far apart, until everything cools and fades to black. For a quarter century, the scientific community treated this big freeze as a closed case, an inescapable mathematical conclusion. But that conclusion depends on a single premise, the idea that dark energy, the force driving the expansion of space, is a perfectly unchanging value. If that force remains constant forever, the cosmos continues to drift apart, and our terminal fate is settled. This premise is the core of the lambda CDM model, the theoretical framework that has anchored our study of the cosmos for decades. The model's rigidity traces back to Albert Einstein. To balance the equations of general relativity, he introduced a fixed variable, the cosmological constant. Physicists are now grappling with a difficult question: what happens to the laws of space if this constant actually fluctuates over time? A 2025 betaset observing 15 million galaxies provides the first evidence. The constant is losing strength. If the cosmological constant is truly changing, then the long-predicted heat death of our universe is suddenly up for debate. Think of dark energy as a mechanical engine pushing outward on a rubber sheet of space. Locked within that stretching rubber sheet are measurable sound ripples left over from the early universe, known as baryon acoustic oscillations. To measure those ripples, researchers built the Dark Energy Spectroscopic Instrument, or DESI. It scans an enormous volume of the sky, tracking the influence of dark energy across 11 billion years of cosmic history. Over its first 3 years, DESI's data release 2 mapped nearly 15 million galaxies, to effectively read the exhaust coming out of that dark energy engine. Analyzing this vast historical record is the only way to determine if the expansion engine is holding steady or losing power. The DESI data indicates a dark energy engine that is demonstrably sputtering. This chart tracks the deviation. A straight horizontal line represents the expected constant force, but new data diverges into a downward curve, indicating dark energy weakens. Combined with weak lensing, supernovae, and cosmic microwave background data, this significance reaches between 2.8 and 4.2 sigma. This statistical range has astrophysicists preparing to modify the standard model of the universe. This statistical anomaly represents the first major structural crack in our current understanding of physics. A weakening dark energy has a specific physical consequence. Eventually, the expansion of space will stop. At that point, the hierarchy of cosmic forces reverses. Gravity becomes the dominant power, pulling everything backward. Distant galaxies would begin accelerating inward, dragging the contents of the universe into a hyperdense, accelerating cosmic collision. The Big Crunch stands as a mathematically viable reality where the specific behavior of dark energy dictates the final physical state of our universe. To confirm an anomaly as a discovery, astrophysics requires a standard known as 5 sigma, a 99.9999% certainty. When the next wave of data from DESI drops, 5 sigma is the threshold the scientific community will be watching for. We are currently engaged in a massive effort to peer into the deepest corners of time to verify this shift. The story of how everything ends is being rewritten while we watch, because the universe has not finished telling us its final